Um, and I'm happy to have you raise your hand, or if you have, I have my chat window open. So if chats come up and questions happen during the lecture, feel free to say it. And I'll try to notice it and answer it. Let me start by sharing my screen, if I can do that. And this is the presentation I'll be giving. It's called A Second Pathway for the Future of Nuclear Energy. Will nuclear energy in the form of fusion be the answer to the world's demand for abundant clean energy? Now, I was invited to write a little piece about this for the United Nations Association of the United Kingdom. It's a group that supports the United Nations and provides promotional and educational information to promote the United Nations mission. And I'll go over pretty much what my article was about. Down on the bottom, I have 2 links. And you should be able to find me by email also. I'm happy to send this slide to you or the entire presentation. You can find me more on my website, which is listed on the bottom. And there's also the article that I'll be discussing that's available at climate2020.org.uk. So let me start by saying Climate 2020 is a annual publication for the UNA UK. The United Nations Association for the United Kingdom is a non-for-profit that tries to promote the United Nations agenda. This is the 75th year of the United Nations. In my view, the coronavirus pandemic has only pointed out the importance of us working as a globe, as a world community. And the United Nations is certainly the organization that is helping people to do that. So there was a agreement from Paris with what's called the 2030 agenda to try to forge an agreement for climate change. And this is what's been motivating the UNA UK in trying to promote public awareness and policy for climate change. They've written several books on this subject called Climate 2020. The first was published in 2018 called Degrees of Devastation, talking about all the horrible problems that we're facing because of global climate change. Last year, they wrote about the Sustainable Development Goals that came out of the Paris Accords, transforming our world to a sustainable system. And this year, they talked about the path ahead. What are we going to do to reach our climate goals? And what I found interesting about this last one that I was involved with is that science and technology and engineering and creative applications of science, technology, engineering are key to the path ahead. We have to be very creative and innovative if we're going to both improve our standard of living and the health of people around the world, and at the same time have sustainable energy that's not going to be damaging our planet. If you click on the website for this, you can download the document where my little article is in, and you can also look at all the other articles. There's about 50 articles covering all the science and technology goals that can be part of our path ahead. So the link for the Climate 2020 is here. It's really well done. Each of the articles are only about 2 or 3 pages long. I strongly encourage you to take a look. And sustainability and energy sustainability, planetary sustainability is a big part of the SEAS program. And many of you students at Columbia SEAS will be involved one way or the other to new technologies that can help have a more sustainable planet. The outline for the 2020 document is shown here. There are about 50 articles. I'm showing 2 pages from the table of contents. I'm going to talk about the one from Guterres, the Secretary General of the United Nations. And then there's a section here called Gray Areas. I'm in the gray area part. And on the second article is called The Second Pathway for Nuclear Fusion. So I'll just talk about mine. But I did want to go through the foreword that the Secretary General of the United Nations wrote in this document. This document came out in April. So most of us were all fully aware of the development of the pandemic. And the Secretary General talked about the COVID-19 crisis as a wake-up call. So these are quotes from his article. It's pointing out that we are a global planet and we have to work together. Things that happen in one part of the world affect all parts of the world. And climate change and energy use is a global phenomenon because any sort of energy technologies that are used in one part of the world will affect the entire planet. And so he also sees this not only as a wake-up call for working together, but as a way that when we make changes in response to dealing with climate change, that we can do it in a way that will lead to a more sustainable planet. And he had 6 goals. First, of course, we have to recover from the COVID-19 issue, which means we need a lot of support for new jobs and businesses. But these new jobs and businesses should be motivated in a way that leads to clean greenhouse transitions. Second, if we're using taxpayers or people's monies to rescue businesses, they should be tied to achieving green jobs and sustainable economy. The fiscal firepower has to drive a shift from the gray economy, which is fossil fuels, to the green economy, which is a sustainable system. Public funds should be used to invest in the future, not the past. Climate risks and opportunities must be incorporated into the financial systems as well as all aspects of policy. What does this mean is that if you are a polluter or contributing to climate change, there has to be financial cost that should be part of that activity. And those costs have to be used by society to help mediate the problems that are caused by that problem. And second, we need to work together as an international community. We see pressures in the world caused by globalization, global trade, conflicts, climate change, the pandemic. And sometimes these seem to be pulling us apart, but obviously the United Nations is using this wake-up call as just the opposite. When we have these global crises, it's better to work together as an international community. Okay, so these are the 6 gray areas that were talked about in the document. I'm only going to talk about one, which is my own, but I want to mention the others. So what do we mean by gray area? Well, gray area means they haven't really been proven. We think these might work, but there's still lots of work to be done. And so the 6 gray areas that were talked about in this document, and every one was very well written, you should take a look. How clean is biomass? The issue of, can we grow grasses and plants in a sustainable way and then burn them for energy and then regrow them, taking the CO2 back out of the air. The one I'll talk about is fusion energy. Storing renewables. Obviously, there has been one of the growths in energy has been renewable energy, solar and wind. It's a very small fraction of the energy use around the globe, but it is growing. If we're going to be more useful in using solar and wind, we have to store that energy for times when the wind is not blowing and the sun is not shining. There's the whole issue of carbon capture, which has been a hope for many, many decades, that we can take the CO2 that comes out of burning fossil fuels and put it back into the ground. What about waste products from our urban environments like New York City? Can we just burn them and take that energy in a sustainable way? And then finally, planting trees. Can we literally take the CO2 out of the air and put it into plants to pull it and ameliorate climate change? So these are the 6 gray areas. I'll be talking about my own. So it was interesting for me to work with this group because this group are climate advocates, people who are strongly committed to sustainable economies and very rapidly addressing our global climate change issues. But they are not, it's mostly a European, this is the United Kingdom. And even though Europe has nuclear power, most of the people involved with this are not in favor of nuclear power. And so a big part of the reason I was invited is many climate advocates would like to have a sustainable energy, but they don't necessarily want to support nuclear power. And so I started the article by the words that I've quoted here. Nuclear power is a contentious topic in climate action circles. And this is a true fact. So climate change really became an issue at the end of the 80s. The first climate UN conference was in 1995. But by then, nuclear power was already supplying about 18% of all the electricity in the world. And, but it wasn't necessarily a leading choice for low carbon energy. Why is that? Because just before 1995, there was the Chernobyl accident, there was the 3 Mile accident, meltdown in America. And then more recently, there was a Fukushima accident because of the tidal wave in Japan. And all of these things are bringing concerns about nuclear power. So there's reluctance to build nuclear power. Most European nations are phasing out their nuclear power, Germany, Spain, Switzerland, and they're taking nuclear power plants and turning them off. So the question that I was asked to talk about is there a second pathway, something that could provide unlimited energy, provide energy that's clean, but do it in a way that doesn't have the risks associated with nuclear power that we have today. So there are 2 types of nuclear power. One is fission and one is fusion. Fission is the splitting of heavy atoms like uranium, and fusion is combining light atoms like hydrogen and deuterium into making helium. And both of these are nuclear power. Both of these produce an enormous amount of energy, but they're very different processes. And so I'm going to be talking about the second one. I won't be talking a lot about fission. I made this slide once when I was trying to explain to the general public about the difference between chemical and nuclear energy. And so all of these pictures are scale pictures of about the same amount of nuclear energy, about 1 barrel of oil. So 1 barrel of oil produces about a ton of liquids of CO2, which if you compress it to 1,500 pounds per square inch and liquefy it, it looks like that big cube on the left-hand side. You can have a big ton of coal. You can have a tank of liquefied natural gas. You can have a big bale of hay. You can pressurize hydrogen into these tubes, pressurized to 4,500 PSI, and all of those produce the same amount of energy. Or you can have a teeny tiny cup of uranium, 3/4 cup, and that produces as much energy as all of the things above. Or you can take, and I have here a glass of water, but I could take a bottle of water that you may be drinking, or you can buy at a store, you can run on your tap. And water contains hydrogen, and it contains heavy hydrogen and deuterium, which is quite easy to fuse together. So every glass of water and every bottle of water contains fuel for fusion energy. It's unlimited, practically unlimited. I made this bottle, and I call it Drink Fusion. And I did some calculations. If you take a bottle of water that's 16 fluid ounces, it has 1,900,000,000,000,000 calories. It has no carbon, it has no waste. It has all these deuterons, which are heavy atoms of hydrogen. And it has more energy than a barrel of oil, or 37,000 laptop batteries, a 1/4 ton of coal, or a bale of switch gas. So every bottle of water contains such a huge amount of energy. And this is energy that would be available for everyone if we had fusion power systems. So I started the article with these quotes: realizing fusion energy. Heavy hydrogen, known as deuterium, is found everywhere in water. If it were used to fuel nuclear fusion power plants, then the entire world's energy supply could be supplied with a small stream of water equivalent to the rain falling across 1 square kilometer. Fusion would give us abundant clean energy, no fuel costs, and no greenhouse gases. And this enormous potential has motivated 3 generations of scientists, and I'm like the third, to try to develop the knowledge we need to realize fusion power. But this is very complicated. It involves immense engineering and brand new physics. And we're getting close. Probably one of the most exciting things on the planet today is ITER, I-T-E-R, ITER. That's how you pronounce it. It's a game-changing experiment. It is the planet's largest applied physics experiment. I'll say it again. It is the world's largest applied physics experiment. It is so large that no one nation could ever afford to build this. The scientists from any one nation wouldn't be knowledgeable enough to do it. It is an international project where the leading nations around the globe are pooling their resources, their scientists and engineers together to build the first fusion energy producing experiment ever. And it's huge. Now, somewhere, if you look very close down here, there is a little person. And each one of these is a story. And this is going to be amazing. The scientists and students at Columbia University are involved in developing the physics and some of the engineering needed for this experiment. Now, this experiment is 70% complete. It's a construction project that started in 2010. It's now 10 years old, 70% done to completion. They just had a video. Let's see if I can, this is complicated. So I have to see if I can do this. I have to do a new share. And I don't know if you can, oops. I'm not very good at this Zoom stuff. Let me try one more time. There we go. Share. Okay, so this is a little movie. It's so cool. It takes 3 minutes. I think we have time. Yeah, I think we have time. It shows you the scale. You can see the people in the yellow work chute. I've been here and walked around the site. Those are pieces. Look how small the people are, how big the devices are. This is what keeps the superconducting magnets cold. It's the largest cryostat ever built on the planet Earth. This was built by Indian engineers and built on site. They provide the steel and the parts. It was assembled on site. And it's the first piece to go into the assembly. These are the large superconducting magnets, the largest superconducting magnets ever built, being brought onto site to be installed. You can see one there covered up with white plastic. They weigh 350 tons. The largest superconducting magnets in the world. Here's another one, number 12 coming in. You can see how large these things are. These are the helium plants to liquefy. This is from China. These are parts from China for injecting gas into the machine. The United States is building cooling systems, magnets for it. This is a magnet assembly center for the large round magnets that go on the outside. All of these are superconducting magnets. That's the heat exchange system. It does not produce electricity, but it will produce about half a gigawatt of energy. And this is the largest assembly. It's 1,250 tons. They raise this up and put it onto the base of the facility, and then they're going to build the experiment on top of this piece of stainless steel. this is amazing in so many different ways. You know, we think of exploring the stars and exploring the deep oceans. Here we are exploring the nature of energy from stars on Earth for the first time. And we're doing it as an international group. And it should be operational probably in about 5 to 6 more years and be producing energy shortly after that. So that was a little video that's only about a week old. Let's go back to my, oops, how do I do this? There we go, share. So I hope you don't mind watching that, but here's a link down here, you can see it yourself. Now, I'm going to change tactics a little bit because I'm a Columbia University professor. I've been doing this for some time now. And about 16 years ago, they made a movie at Columbia about controlling fusion. And that movie was called Spider-Man 2. It takes place at Columbia University. Peter Paul is a applied physics student studying at Columbia. Oops, I have to go back, turn that off. There we go. And he meets up with a scientist who is making fusion energy just outside the main part of campus. And this is a picture of this experiment. I'm going to see if I can show it. And that's him making a small sun on Earth and controlling it with mechanical actuators. This will produce about twice as much energy as the ITER device in this made for Hollywood sequence. Now, as you probably remember what happened, this thing had some problems and it started having control issues, and the plasma started destroying the laboratory around it. Of course, this is a very bad thing. We don't want that to happen. And let me go back and show here. And so I want to talk about this a little bit before we get into what we actually do by asking you if you've seen this movie. If you haven't seen it, you should see it. If you have seen it, then what is wrong with this picture? And I'll say a few things about it. First of all, this is the fusion device, which for Hollywood makes it look like our sun. Our sun is very, very big, and there is no way that you can confine a plasma at hundreds of millions of degrees in a small ball like this, because the pressure of the plasma inside would be so great, there's no way you can confine it. So it'd be impossible in a sphere to control a plasma at this size. The second thing is there are instabilities at the edge, these little loops that are coming out. These are sort of magnetized plasma loops. But there's also no way to control that plasma by having mechanical actuators, because the plasma is at 100 million degrees. If it touches anything that's metallic like this, it would instantly cool and the plasma would turn off. So the control system has to be done without ever touching the plasma. And you can never confine a spherical plasma like this in a small laboratory. Let's put this in perspective. So if we look at our sun, you can see the scale of the sun compared to Earth. Earth is that little round ball here. This is the sun. These are the magnetized loops. The sun generates its own magnetic field. And these magnetic field lines actually confine plasma. The hot charged plasma or ionized particles that are inside here, this is heated up to about 24 million degrees. All of these tend to follow the magnetic field lines and make these arcs. And you can see that magnetic fields confine plasma along the lines of the magnetic field. But of course, when they get close to the South Pole or the North Pole, then it would strike back into the source of what that plasma is. The reason the sun can confine this spherical plasma is because of obviously it's gravity. But in order to have gravity sufficient to confine the hot plasma for fusion, you have to be about the size of a star. You can't do it on Earth. So we've been doing something else. At Columbia, around the world, and in ITER, we use the strongest possible magnetic force fields. We make very, very large magnetic fields, the largest magnetic fields you can make on the planet Earth. And instead of using gravity to confine the plasma, we use very, very strong magnets. Now, of course, to make a magnet, you could run current through a piece of copper wire, but the copper wire would get hot because of its resistivity. The great advantage of fusion research today is that we know what superconductors are. Superconductors produce magnetic fields with large currents without dissipating any energy. And so they essentially are perpetual motion machines for magnetic fields. And so the reason we have a hope of making fusion power using these very, very strong magnetic fields is because we now know how to make superconducting magnets. Now, we're in the applied physics department, and the applied physics department does all this complicated mathematics, magnetostatics, Maxwell's equations, and things like this. And so we showed 50 years ago what the physics of confining plasmas with magnetic fields are. And it turns out the physics, all the equations from Maxwell's equations to the equations of forces on plasmas, says that you must confine a plasma with a magnetic field with a torus. The only configuration that works is a torus. It has to be the jelly of a donut. Okay, so this is a picture of magnetic fields that we created, and the plasma is this jelly of the donut inside, and this is where all the fusion happens. And we go back and look at ITER, the pink glow in this picture is where the fusion energy happens. Okay, you can't confine plasma with a sphere in the laboratory. You can only use something like this of the size of a star. So this is what we do. We use magnetic forces instead of gravitational forces, and we can find these hot plasmas at hundreds of 1 to 200 million degrees until it makes fusion energy. Now, we've done this. The first experiment to make fusion energy was at Princeton University. I was there. Very, very exciting. It was done in a machine that on a scale drawing is this size. You can see inside here, most of the stuff these are heating devices over here. This is the vacuum chamber. The plasma was a toroidal thing on the inside over here. These are magnets on the outside. You can see here's a scale model of a person. This experiment worked in the 90s and has now been decommissioned. This is the joint European torus, which operated shortly after this. You can see by scale, they're about the same size. These little copper things on the outside are part of the magnets that are associated with making the strong magnetic field. Both of these devices worked for a short period of time because the magnets were not superconductors. They were just literally copper magnets that you might make in any sort of motor. And you can see the size, and they both worked. They produced strong magnetic fields, they heated the plasma, and they produced fusion energy. This is ITER on a scale drawing. You can see how much larger ITER is than these. This is because ITER has to be the size in order to produce net energy. These experiments did not produce net energy, but they did demonstrate the principles that make fusion work. By the way, the magnetic field on Earth is about 50 microtesla. The magnetic field on ITER and some of the peak magnetic fields on both of these devices were the order of 10 to 12 Tesla, which is about 250,000 times larger than the magnetic field on Earth. And if you've ever played with magnets, you take a magnet and you hold them together. And if you have a North Pole and South Pole, they're attracted to each other. But if you have a North Pole and North Pole and you push them together, you feel a force. It's a force field, an invisible magnetic force field. And that pressure is proportional to the square of the magnetic field, B squared, B times B. So if you have a magnetic field which is 240,000 times larger than the Earth's magnetic field, then the magnetic pressure is that squared, which is, like 1 trillion times more pressure than the Earth's magnetic pressure. We are making the largest magnetic field ever produced on the planet Earth. These are pictures of the fusion power generated by these two devices, the TFTR device at Princeton and the JET device at Cullum, England. And they produced about 10 to 15 million watts of power. That's enough power to heat 1,000 homes. That's not bad. They would do this for just a few seconds. The longer pulses would happen at lower power. If you increase the power more, they could not sustain that for long periods of time, which demonstrates something about, the power and the time configuration. But nevertheless, established, we studied this at depth. We know everything about the fluctuations, about the plasma, how to create it. We learned a lot about how this works and used that to design the ITER experiment. Now, the key to making fusion are superconducting magnets. Magnetically confined fusion requires superconducting magnets to hold in the hot star. We can't use gravity, we got to use magnetic force fields. Niobium tin is a superconductor that was discovered in 1954, and the ITER device is made with niobium tin superconductors. It looks a little bit like the drawing over here. I've also done experiments. I've built superconducting magnets with niobium tin. They're beautiful. It's very complicated. It's hard to imagine what these are, but if you look, these are strands or wires of niobium tin superconductor. These little holes around it allows liquid helium to flow through to keep it at cryogenic temperatures. And this big jacket is stainless steel, which is used to hold the magnetic forces of these superconductors. If you look at each one of these wires, it looks like this. And inside each one of these wires are tons of little itty bitty wires. Each of these wires are like 30 micrometers of niobium tin superconductor inside a copper mesh. And that's what carries all of the current. So this was discovered in 1954. We learned how to make these magnets. And these are the sort of magnets that are being used in the ITER device for the first time at large scales. Now in 1986, we discovered a more powerful superconducting magnet, cuprate superconductors. These are called the high temperature superconducting magnets. And we're just beginning now to learn how to make them. And some of the scientists in this country, in the United States, and in the United Kingdom are building fusion magnets using a magnet which is even stronger than the magnets that you can produce with niobium tin. We'll see how this works, but this will make fusion even more exciting. Now so we discovered in 1954 niobium tin. We learned how to make superconductors, and then it took us about 3 years, 1985, 1987, to actually build our first superconducting magnet, Taurus. This was a joint project with Westinghouse, General Electric, European Union, Switzerland, Japan, General Dynamics. They all built these magnets. And you can see the scale. There's a person, these are the magnets. And there's the first large toroidal test of magnets for fusion. After this was done in 1987, in 1988, we started designing the ITER experiment. It took decades to finish the design. And now we are building ITER, and ITER is literally 70% done using this technology that was demonstrated here in this international facility. Now, I told you that the new high temperature superconducting magnets are even better, and there's research at Columbia trying to enhance the ability of these magnets to work in fusion. But you can see here I have a little arrow. These down here are the magnets that are used for ITER. They're low temperature superconductors. This arrow, and this is a log scale, shows that you can increase the performance of these magnets by 10 times the magnet, 100 times the pressure by using high temperature superconductors. So a real race is going on in the superconducting magnet community to make the largest, strongest magnet you possibly can for fusion. I have about, a little bit of time left, and I want to talk a little bit about the experiment at Columbia. So Columbia University has been a pioneer in understanding magnetically confined fusion. And we have an experiment on the first floor of the Mud Building. I hope some of you had a chance to see it. I put this in a scale drawing over here. You can see the HBTEP tokamak, which is at Columbia, is shown in that little box with the arrow. It's teeny. It's teeny compared to ITER, but it has all the ingredients for us to study how to make the plasma, how to control the plasma, what the physics of the plasma are. And we've had students exploring the microphysics and the macrophysics and the control physics associated with fusion using the device at Columbia University. I don't know if any graduate students are on this lecture. I think this is mostly for undergraduates. We do have undergraduates working with us, not at the moment. This week, as many graduate students know, we are now opening up the campus again to essential research. And this research is supported by the US Department of Energy. We have obligations. And so we're beginning to get our graduate students and our scientific staff to start up this experiment again after the shutdown associated with the COVID-19 shutdown. Here's a close-up of the experiment. It's Columbia University's real-life fusion control experiment. It's a marvel to look at. It's totally safe. Well, not totally safe. We operate in a totally safe way. It does require making a fusion plasma. We heat it up to about 10 million to 20 million degrees. That's 20 million degrees is hot enough that requires a lot of energy. We use pulse power. We charge up big capacitor banks to store that energy. And then we dump that capacitor bank into the magnets, which produces the energy associated with making the plasma. The plasma heats up to about 100 to 200 million degrees, and it stays that way for about 1/100th of a second. During that time, we measured every 2 microseconds and record all the dynamics of how the plasma operates. In addition, we have real-time active feedback controllers that are used to control and diagnose the plasma. And what you're looking over here is a schematic of the torus that you see here. And all these different colors, green, blue, black, and red, are all ways in which we use to control and manipulate the plasma. These are the 3 older graduate students who have been working on the experiment. We have Alex, Ian, and John. They are working with younger graduate students and with our undergraduates. You can see how big the experiment is compared to the ITER device that I showed earlier. Over on the right-hand side is a picture on the inside of some of the diagnostics. So this is a slice through the torus, and the plasma goes around on the inside, and all around the edges are these little boxes. These boxes are stainless steel shields that protect the sensors. And those sensors are used for understanding exactly how the magnetic field of the plasma surface are changed with time. And we use that to understand dynamics and also to feedback and control that dynamics. Now, a big part of this experiment are all of these little windows that you see. And on each one of these windows, we have magnetic coils. And if I can just go back up and remember that these plasmas tend to have perturbations that come out. And in Spider-Man 2, you use these pieces of metal to try to push the plasma back in. But this is impossible. So instead, what we do is we use magnetic force fields. And each one of these is like a little controller. And when we energize a coil, it pushes onto the plasma and pushes the plasma away from the wall. And we have this surrounding the entire plasma. And Columbia University pioneered the use of these multiple high-speed feedback controllers to control the magnetic perturbations at the edge of the plasma. Since that time, there's many other facilities. We have the ITER device I told over here, and all around ITER are all these little coils that are used to apply magnetic perturbations to the ITER device. This is an experiment that's coming up at Princeton. It's called the National Spherical Tokamak Experiment. We have Columbia students who are working there, and some of our undergraduates have worked there as well. And I'm showing a picture with some of the red coils and blue coils that are located around on the inside that are used to manipulate and put forces onto the plasma, not by the little hands that Spider-Man 2 is doing, but by magnetic force fields. And then here's the D3D device in San Diego, which Columbia students also work on, and Columbia faculty. And these are some of the coils that are mounted on the inside. These are coils over here. And each one of these, when they energize, provide a magnetic field that pushes back on the plasma to control it. And this is what we do in real time to keep the plasma perfectly toroidal and staying on the inside. We have lots of undergraduates and students who work in our experiment. I show here a picture of 2 students who built our experimental controller. They're very proudly showing the hardware that they built. These are actual things that the students built themselves. This is a group of undergraduate students who went to a conference at Princeton talking about research and learning about plasma physics. And this is a large conference that was done recently with our students presenting posters at a scientific conference. And so all of our students participate in the operation, technology, construction, maintenance of this experiment, but they also participate in conferences where they present their research topics and what they do. Now, the last part of the article that was in the United Nations Association Climate 2020 was titled Research Beyond ITER. And so our research at Columbia University is focused on the control of the plasma and making the fusion energy. And ITER will be the first test of producing large amounts of energy for long periods of time, several, half an hour for each pulses, using the largest superconducting magnets ever made on Earth. But much must be done in addition to operating ITER if we're going to make fusion work. Around the fusion device, this essentially is like a sun. And there are spots of the chamber where the heat flux coming out of our magnetized star is comparable to the heat flux at the surface of the sun. And think of how challenging it would be to be next to the star, our Earth, our sun, and keep something so that the material doesn't evaporate. So cooling the edges and removing the heat and preventing the evaporation of materials at the surface of a star is a big problem. That energy has to be pulled out for making heat. In addition, as the energy comes out, we have to generate electricity. And the most effective way of producing this fusion is to take some of the neutrons that come out of this and turn it into tritium. And that tritium must be constantly recycled and put back in. So all of these are nuclear energy technologies that must be perfected if we're going to make fusion work. And so this is the conclusion of my report. There's a long road to commercialization. Even with strong international support from governments and the growing participation of private industries, the race to commercial fusion energy is a marathon, not a sprint. We're not going to do this quickly, but we can't give up. It's a marathon, not a sprint. We've developed a new science of magnetic fusion confinement, and we have new technologies that make fusion economically attractive, but it still requires decades of research and development, especially these technologies associated with the nuclear technologies that go beyond ITER. Now, if we have near-term climate concerns, the world wants to solve our sustainability issues within 10 years. And that will not be addressed by fusion energy. But we can't look just 10 years. We have to look longer than that, because if history is our guide, we know that energy is going to grow beyond what we need in the next 10 years. And so the goals of scientists like myself and engineers is to meet the long-term energy needs for fusion producing energy. This is to use energy that is everywhere, using energy that's practically limitless, and to essentially make our star at Earth using the highest possible superconducting magnets we can, and using technologies that will really make this a safe and sustainable energy source. So that's the end of my presentation. I hope you enjoyed it. There's lots of links in here. If you send me an email, I'll send you a copy of this talk. And I wish you all the best this summer. I can't wait to see everyone back on campus later on next year in the fall. And thank you very much.